but it's important because I'm going to explain why we need to study this subject. So, for example, I'm going to talk about motivation, like why we are studying this subject, what's the importance of this subject, and why bother, studying. And mechanics of material, it has two words in it. I mean, three, but two. So it has mechanics and it has materials. So you know what material is. Like everything is made up of material. This table is made up of material. Chair is made up of material. So we have an intuitive understanding what material is. So material is basically like every object or a body is made up of some substance. That substance is called material. So yeah, so that's like we know what material is. So we need to know what mechanics is. So that's how we can understand. So what we're going to study in the subject is mechanics of materials. So we're going to see what mechanics is, how the subject fits where. So yeah, mechanics is basically a branch of physics. It's a major branch of physics. So everything, all like physicists talk about is basically like mechanics. So mechanics is a major branch of physics. So we're going to talk about mechanics, but from the perspective of materials. We're going to cover some general principles of statics. It's basically going to be a revision of what you guys have studied in the previous subject. So everyone has taken the static class in the last semester. Okay, so yeah, so we're going to talk about units of measurement because it's important. You need to do calculation. You need to know what unit is, how we measure, what are like systems of units, which you guys already know, but it's going to be a revision. Then we're going to talk about loading types. And when we'll talk about loading types, you will have a clear idea about what chapter talks about what thing. So, I mean, there are different loading types, and different loading types have different stresses and strains. So once we'll cover this, I think you will have some idea which chapter is about what topic. So you have like more clear understanding about the things. And then we'll talk about sign convention because it's important, in statics also, you need to know which force is positive, which force is negative. So it's important to set some rules. It will better help you do the calculations easily. Okay, so I'm gonna just tell you a little story just to highlight the motivation. So it's an actual story. It happened in 1912. So there was a ship. It was one of the biggest ship of its kind. So it was going from Southampton to New York. So the date was 1912. The day was April 10th, and the ship started its journey on that day from Southampton. It was going to New York. It was one of the biggest ship ever built of that time. It was 269-meter in length. It was one of the most luxurious and biggest ship. It was carrying 2,200 passengers and crew. And some of them were like actors, some of them were immigrants, some of them were like famous people. Like so, it was a big deal. And the cost of building that ship during 1912 was $7.5 million, which is about $500 million today. So it was a big, expensive ship. The guy who was uh, running the ship, who was responsible for carrying the ship from Southampton to New York, he was Captain Edward J. Smith. He was 62 years old at that time. The ship was built by a company named White Star Line. So the vice president of that ship, his name was Philip Franklin. He said the ship is so strong. We have built this ship like it's never gonna sink. It's like super strong, and don't worry about it. And the ship started its journey. After 2 days, the ship received some warnings. And by the way, receiving warnings is common when you're in a cruise. Uh, Nearby ships, they see snow and an iceberg. They radiate the signals, and they let you know like there is icebergs ahead, so be careful. So the captain was like, okay, I mean, not a big deal. So we'll just continue moving from the same speed. So the ship started moving it was moving in the same speed, like 40 kilometers per hour, which is 21.5 knots. And after 2 days, they received seven more warnings. So the captain was like, okay, I mean, it looks like we have a lot of snow ahead. So let's just like maneuver a little bit. So he just started maneuvering a ship, but he didn't reduce the speed, even though we received like seven more warnings. So during that time, I mean, we already have sensors in the ship to let you know if there are icebergs ahead, but still, it was, I mean, it was not that strong. So they had a guy in front of a ship which was looking from his naked eye to see if there is some iceberg, and then they're gonna let the ship know, and they can maneuver the ship around the iceberg. But it was like 11:30 p.m. It was night. It was super cold. So the guy, Frederick Fleet, he was maybe not attentive, or he couldn't, see the iceberg. So it was too late. He sounded the alarm, but the ship just hit the iceberg. So it sank. So the unsinkable sink. So I'm talking about Titanic, by the way. I don't know if you guys have seen the movie. Yeah, so it's about Titanic. So on April 15th, the unsinkable Titanic sinks, by hitting an iceberg. So as a result, 1,500 people die because the ship could not take the impact from the iceberg. So why I'm telling you this story is because it has a lot to do with the subject. Because the ship hit the iceberg. So ship is made up of steel. Steel is a material, and it has to do with the material properties, for example, ductility, strength, toughness, deformation, and all of these things which you're going to study in this subject, that will let you know how tough the material is, or how it can take an impact or not. So the subject is important. And I mean, one of the reasons the ship failed was, like, there are many reasons, but it was too brittle. The steel during the, like, ice, if you're at negative temperature, steel become brittle and it can break. I mean, if it has an impact. But we're going to talk about brittleness, ductility, and all the material properties which are important. So that's a catchy definition, but that's how it is. Like, mechanics of material is a subject that teaches you how things break, so that you can spend your career making sure they never do. I mean, just it will you will have a better understanding about the materials, and you can, like, appreciate, and you can figure out, like, which material will fail when and how much load is needed, so you can just barely put enough load so that the material, I mean, the things don't break. So that's the beauty of this subject. So you will learn more about materials, you will learn more about the loadings, and you can, like, better prepare yourself, because later, I think, uh, how many are civil engineers? I'm a civil engineer, by the way. How many are mechanical engineers? Okay. And what other people are? You have biomedical, you have construction something. So that's, like, I think mostly are from civil and mechanical. Yeah, so I mean, it's super important for, like, civil engineers. It's super important for mechanical engineers. The subject founds the basics, and you're gonna, for example, for civil engineering, you guys have already studied. Everyone has already studied statics. This is the static was the foundation. Now you're gonna study mechanics of material, and from here you're gonna study structure analysis and stuff and design. So yeah, so everything which is coming ahead needs the basics which you are going to study you have already studied in statics. You're going to study in mechanics of materials. So super important course, super foundational. So, and it's going to be fun, I guess. It's similar to statics. We're going to do a lot of calculations. So yeah, so what is mechanics of material? It is statics, which you guys have already taken before, and we're going to add bunch of new stuff, which is, we're going to see how things deform when you have applied loads on it, and we'll see how things fail, why things fail, and how we can prevent the failure. So for example, for civil engineers, you need it for designing of buildings, you need it for bridges. For mechanical engineer, all sort of machinery required you to know the material behavior, and, like, all the other engineering disciplines as well. So we know what material is. We need to know what mechanics is. So mechanics is basically, uh, it's like there are principles of mechanics which are at play, and that's why how, like, things happen. For example, uh, so material is any substance that constitute a physical object. I mean, for example, everything is made up of material. So object is made up of material. So I mean, it's pretty clear what material is. But the principles of mechanics are the laws, you can say laws of nature or laws of physics, that makes things happen. So for example, if a plane is flying, It's flying because of the principle of mechanics. If machines are working, they have all the things, and they have to combine, work together. So if machines are working, they're working because of the principles of mechanics. If the buildings are standing, they are standing because of the principles of mechanics. So anything happens, that happens because of certain laws. That laws are defined by Newton, first law, second law, gravity, stuff. So there are physical laws which are there in this nature, and that's called principles of mechanics. So everything happens because there are set rules to this like world. So that rules are under the principles of mechanics. For example, if you're walking, you're also using principles of mechanics. So you're using basically Newton's third law. I mean, you're pushing the ground backward, and as a result, your ground is pushing you forward. So that's how you walk. You're using third law, Newton's third law, to walk basically. So yeah, so we use these principles in all sorts of engineering. We use it for mechanical engineering. For example, we're going to use this subject and these principles of mechanics to design, analyze, and optimize mechanical systems and components. We use it in civil engineering to design, analyze structures and such as buildings, bridges, and roads. By the way, this is one of the example. I mean, we use it like everywhere. After when you're going to do internships, you're going to do jobs, you're going to use these principles like all the time. Aerospace engineers use it for designing and analyzing aircrafts and spacecraft. Automotive engineering, they use it for designing and improving vehicles. You have material engineers. Do we have any material engineer here? No one. So yeah, so material engineers basically understand behavior of materials, and they develop new materials as well and improve the existing ones by using these principles. You have robotics and automation, which they design robotic systems and everything, optimizing control algorithms. And by the way, you don't need to remember anything. I mean, just it's not going to be a part of exam. It's just like I'm trying to give you guys a motivation, like why you need to study the subject. So when we'll do calculations, that's going to be a part of exam. So this is just for you guys to just it's first lecture. So and we use it in manufacturing engineering and all sort of engineering basically. So yeah. So I'm gonna talk about, because we know materials, I'm gonna talk about mechanics a little bit. I'm gonna talk about history, and then I'm gonna talk about branches, and then you're gonna see like where this subject basically fits in the whole realm of physics and science. So what is mechanics? By definition, mechanics is a branch of physics, and it's one of the biggest branch of physics that deals with the effect of forces on bodies. So body, basically, when I refer body or object, it means, beam is a body, truss is a body, table is a body. Any object which is made up of some material is called a body. So mechanics is a branch of physics that deals with the effect of forces on bodies. So basically, when, for example, a truss, you apply a force on a truss, what happens to the truss, what are the reactions to the truss, what is the internal forces to the truss, uh, all of this comes under the branch of mechanics. So mechanics, so that's the definition. Like it deals with the effect of forces on bodies. So you have forces and you have bodies, which is truss or beam or column. And then what happens when forces are applied on a body, that's what we study in mechanics. It's super big field, super important. So in history, like it all started very early in ancient. So so mechanics has like three eras. One is ancient foundation, and the second one is the classical physics, and then you have like newer version that's like quantum mechanics and stuff. So the very early scientist, Aristotle, he started thinking about mechanics or physics or how the world works. So he was like, maybe he thought that it's like the force is continuous and the vacuum is impossible. So these are some of the early ideas of physics and science and mechanics. And the early ideas were speculative. So basically, they were like, they didn't know how to quantify things. They were like, okay, maybe that's how it is. Maybe we can see things happening and that's how it happened, but they cannot quantify it. And then Archimedes is also one of the famous thinkers and philosophers in our field, and he really like started the field of quantitative mechanics, and he pioneered like statics, which you guys have studied in the previous semester, and also hydrostatics. And he's also famous for his principles of levers and Archimedes principle of buoyancy. So basically, I mean, he was the guy who said like, give me a lever and I can move the earth. And also like during those time, like it was time where you had kings. So it's also a very interesting story about him, because there was so a king had gold, and the gold, he was worried that maybe the people who are holding the gold, they are stealing it. And how they're stealing it is like they're taking out some part of the gold and they're mixing it with other impure elements like metals and stuff. So he asked him that, can you do something about it? I need to know if my gold is being stolen or not, but I cannot figure out. So he used his principle of buoyancy to figure this out. So it's very interesting. If you guys can search about it, like it's a nice story. And in 980, like common era after Jesus, then like Ibn Sina, he also developed like concepts of inertia, like how things work. If you're moving, it's gonna keep on moving. And he talked about like vacuum and stuff. So this was all like primitive, like ancient foundations. And then the second like era is scientific revolution. So then comes the scientific revolution, and then comes the classical mechanics. And we're gonna talk about classical mechanics. We're gonna talk about these concepts in this subject. So Galileo was the first one. He was like, he talked about like falling bodies, inclined planes. He talked about laws of inertia. So he's pretty famous scientist in this field of physics. And then you all know Isaac Newton. Everybody knows, right? I mean, he published his laws in Principia Mathematica, and he published the book in 1687. And yeah, so he presented his laws of physics. And as far as we are concerned, we're going to follow Newton. We're going to follow his equations to solve all the equilibrium equations. So by the way, in statics also, you were using like summation of forces is equal to 0. That's his third law of motion. And then there are a bunch of other scientists, maybe Maxwell, Hamilton, all contributed in this field of mechanics. And then comes the like what's happening nowadays. So it's modern physics. Modern physics, it started late 19th, early 20th century, and there are some limitations to the classical physics which uh, they started to solve. And then the two major fields come out, like new fields. So one of the major scientists is Max Planck. He like pioneered quantum physics theory, which comes under the mechanics. And you all know Albert Einstein. So he said like Newton is not true. I mean, gravity is not a force, and time is not constant, and everything is relative. And he formulated his like special relativity and general relativity theory. So, and then there are some newer scientists who are like advancing this mechanics field in quantum mechanics and stuff, and the work is being continued. So nowadays you have quantum mechanics, you have general relativity, you have chaos theory, and so they're still working. This is, I guess, one of the most famous picture ever taken in the science community. So these are like the newer guys. Maybe you guys know Einstein, you know. So maybe, I don't know, you have studied Bohr atomic model. This is the guy who's Bohr. Schrodinger cat, Schrodinger equation. This is the guy. So yeah, Marie Curie, she discovered radioactive uh, things. So almost, I think more than 90% of the guys, like more than everyone, got the Nobel Prize. So yeah, so these are the scientists who are like who extended the field, and everyone is still working on newer stuff. So the evolution continues. So we talked about like three major eras, and every era has a different field of mechanics. So during the scientific revolution, there was classical mechanics, and we're going to talk about classical mechanics in this subject moving on. But just wanted you guys to know that we have other branches as well. So classical mechanics are the laws of nature which works during common this like on our level, everything works according to the classical mechanics. But if you go really big, like you talk about celestial objects, you talk about, black holes or, sun and stuff. So Einstein laws works better, than the Newton. And if you go really, really down to subatomic level, then the laws doesn't work. Like the gravity is different, the laws of motions are different, everything is different. So it doesn't work like it works under the classical mechanics, like you and me can observe. So it's about quantum mechanics. So these are the three things. We're gonna focus on classical mechanics in this subject. So yeah. So let's focus on classical mechanics. So classical mechanics. So now I'm trying to explain you guys where this subject and engineering mechanics statics basically lies. So what is mechanics? Mechanics is a branch of physics that deals with the effect of forces on bodies. So you're gonna have trusses, beams, you're gonna have forces, and then you're gonna see what are the effect of those forces on those bodies, which is beam, truss, or column. And that studying is called mechanics. And mechanics have three branches basically. You have rigid body mechanics, you have deformable body mechanics, and then you have fluid mechanics. So rigid body mechanics is basically an idealization. You assume that the body, which is a truss, a beam, or a column, it will not deform. And that was an assumption when you were doing engineering mechanics statics. So when you were studying engineering mechanics statics, the subject which is prerequisite for this, you assumed that the bodies does not deform. So when you had truss, you had loads, you calculated reactions. So you didn't worry about the deformation of the individual truss element or the beam or the column. So that was an assumption. We're going to remove this assumption and we're going to see if you allow body to deform, what happens, and it will happen like it will deform, 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 and it will fail. And you don't want that. So deformable body mechanics, which is this course, is all about mechanics, all about what you have studied before in static subject, but we're gonna remove the assumption that the bodies now can deform. So now you're gonna have additional layer you need to investigate more, and it's important. For example, you're calculating, deform. You need to calculate the deformation as well. So that's what we're gonna do in this course, in addition to what we were doing before. And fluid mechanics, in fluid mechanics, the difference is that the body is a fluid, so which is like out of scope of this course. So rigid body mechanics have two branches, statics and dynamics. And statics is something which you guys were studying in the last semester. So that's what you studied. So I don't know if anyone has taken dynamics course or is willing to take or is gonna take dynamic course in future. So the only difference you're from mechanical? Biomedical, yeah. So in rigid body mechanics, you have two branches, statics and dynamics. Statics, everyone has already taken, and the static is the body is static in a static position. So you have, for example, beam or a truss or any component of a machine. So your assumption is it's rigid, it's not gonna deform, and your assumption is that it's static. So if you make these two assumptions, whatever you study comes under this statics, which you did it in last semester. And when you remove the assumption that the body can move, for example, if a car is accelerating, then but it's rigid, then you're going to study in dynamic subject. But we're going to study mechanics of material. So mechanics of material is everything statics, but the assumption in statics was that no deformations. So we're going to remove this assumption, and now when we're going to see forces applied, in addition to calculating reactions, we're going to also see how what's happening inside the body, what's happening, what are the stresses, strains, how the material is deforming, when it will fail, these kind of things. So it's an additional layer of concepts you need to know to figure out additional stuff. So that's what mechanics of material is all about. So yeah, so what is mechanics of material? It's statics, which you guys have already studied in the previous semester, and you're going to add concepts of deformable body mechanics, which if you disintegrate further, you need to know like fewer newer concepts in addition to what you've already studied in statics. So in statics now you already know how to calculate reactions, you already know like constraints, and you can you know the loads, you can calculate the reactions. Now you also need to know what happens inside the body, what are the stresses and strain, how the body deforms when the load is applied, and how it will fail. So that's like a next step from the statics subject. So that's the bookish definition which is written in the book. So that's the definition. That is like mechanics of materials, some people also call it strength of materials, is a continuation of statics. So where materials are allowed to bend, deform, and yield. So in statics, the materials were not allowed. We made an assumption that the materials will do not deform, do not bend, do not yield, and do not fail. But now we're going to remove this assumption, and we also have to keep in mind the materials will bend, deform, and yield. So we need all those concepts which I explained in course description, and you need these to calculate failure, to calculate bending, to calculate all these kind of things. Yeah, yeah. So that's the subject, and hope you guys enjoy this subject. I think it's pretty important, and for now, yeah, we'll see in coming lectures. I'm going to give you homework, but this is not a part of exam. This is just an introduction for you guys. And see you in the next lecture.